Merci Gilles. Bonjour tout le monde. Good morning, everyone. Our project is about cumulative environmental effect and resource development on watersheds already impacted by mine development. Okay, the cobalt mining camp is located within the watershed of Far Creek, which drains to Lake Temiskaming, and Lake Temiskaming is part of the Ottawa River system. Now, the cobalt camp was the scene of a wild silver mining boom at the beginning of the 20th century. And at that time, there were no environmental regulations. So every mine simply discharged their tailings to the nearest lake. And that's what you see in this picture there. And this has resulted on pervasive and ongoing metalloid contamination throughout the watershed. The main contaminants of concern are arsenic, cobalt, nickel, and antimony derived from the fairly exotic mineralization of the vein-type deposits, which are mainly arsenides and sulfur-arsenide minerals. As the name of the camp implies, cobalt was a significant byproduct of silver mining. And because cobalt is of such interest nowadays for electric vehicle batteries, exploration companies are renewing their interest in the camp. And that raises the question, how would you assess the environmental impacts of new resource development against such a background of pervasive contamination? Now, in our project, I'm going to address today, in the interest of time, just 3 points, 3 components. One is concerns point sources of contaminants from the Shaft 98 of the Nipissing mine, distributed sources of contaminants from the Crosswise Lake tailings, and the ultimate sink for contaminants in sediments at the bottom of Lake Temiskaming. The first component of our project concerns metalloid loading in mine waters discharging to surface waters. And the photo there shows the artesian discharge of mine water from the Nipissing mine and the flume where we measure the flow and where we also sampled water quality on a weekly basis. The research question was to understand the relationship between the concentration of contaminants in the discharged water and the discharge rate. And this involves the interplay between chemical reaction rates for the weathering of these mineral hosts and the flow rate. And this interplay is characterized in the chemical literature by what's known as a Dan-Kohler number. Interestingly, the study of concentration discharge relationships originated in catchment hydrology, where they were interested in simply landscape weathering reactions. Now, the objectives of our study here were to develop models for predicting metal contaminant loads and concentrations from flow monitoring data. And specifically, it'd be nice if we could predict using this model how metalloid mobilization will be affected by extreme flow events related to future climate change. The upper plot shows the hydrograph of discharge at the collar of the shaft, and the red and green chemographs are for total and dissolved arsenic. The bottom plot shows the arsenic, the hydrograph and the cobalt chemograph. And it's interesting to note here that there is a lag between peak concentrations of arsenic and the peak discharge from the shaft, whereas there's very little lag for cobalt, which suggests that there are different mineralization kinetics involved for these two different metals. Here's some examples of concentration discharge relationships. On the left, arsenic versus flow rate, and on the right, cobalt versus flow rate. And both of these metalloids show an increase in concentration as flow increases. And this is indicative of what we call flushing. If the concentrations decrease, we get sort of what's known as a dilution effect. The beta value is simply the exponent on an empirical power model, and it's used to characterize the strength of the flushing. And you can see these values are pretty low. These two figures essentially confirm the low variability of arsenic and also cobalt in the sense that the arsenic load, that's the concentration times the discharge, is really totally dominated by the variability of discharge. And the plot on the right there shows arsenic load versus discharge rate, and there's a nice power law model fit. Moving now to task 2 of the project, which concerned the stability of legacy contaminants in wetlands and lake environments. We sampled mine waste, sediments, and surface waters, both upstream and downstream of mining impacted areas, to look at the concentration and speciation of these metals of concern. We also conducted some micropaleontological analyses of lake sediments to evaluate the ecological response to contamination throughout the sediment column. Now, the results will be used to assess pre-mining baseline concentrations, a lot of these elements of concern, the influence or the impact of past mining activities, and the extent of any post-mining recovery. The bathymetric map there on the right shows the outlet of Far Creek and the location of lake sediment cores that Mike Parsons, Josue, and others obtained in March of 2022. And here's some results from lake sediment cores. Here are a series of depth profiles in the lake sediments showing peak metal concentrations at a depth of about 70 centimeters, fairly consistently for all these different types of different metals. We age dated the lake sediments using different methods, and it was found that peak metal concentrations were deposited probably in the 1930s. Taking a look now at some of the micropaleontology work, the photos there show the different types of arsenons or different bugs that were encountered in the lake sediments, and they are used to assess the ecosystem response to changing metal concentrations over time. This fairly complicated plot I'll walk you through. It shows depth profiles of abundances for different arsenons. And some of these arsenal assemblages are indicative of stress conditions, and others are more reflective of healthier conditions. So in green, it's the pre-mining phase. In red, it's the peak mining phase. Yellow, it's declining mining. And blue, it's post-mining. And what you see is really a strong contrast between the pre-mining and peak mining, where arsenal assemblages characteristic of stress are dominant. Finally, the third component of our project is concerned with the mineralogical characterization of mine waste, and I'm going to focus here exclusively on new tailings core samples we obtained from Boswell's Lake. We conducted analyses of physical properties of the tailings, but also we looked at the primary and secondary minerals that are found within the tailings. This is a satellite image of Crosswise Lake showing the big deltas that form from the discharge of tailings straight into the lake. And I also show there the locations of some of the boreholes that we drilled. Here are some of the minerals that are fairly ubiquitous within the tailings. A signature mineral of the cobalt mining camp is ferrite, a cobalt nickel arsenate mineral, which is derived from the weathering of sulfur arsenide minerals. And there's cobaltite, which is one of the primary minerals in the veins, and also chlorite and plagioclase, which are ubiquitous gangue minerals. On the left here, there's a depth profile of cobalt concentrations in the tailings, and we find peak cobalt concentrations of about 3,000 ppm at a depth of about 3 meters. The bar charts there on the right show the mineralogy of samples at different depths, and we see that the peak mineral, the most important mineral in the clay fraction is chlorite, perhaps not surprisingly, but plagioclase is also important. But I draw your attention to the pink mineral, which is erythrite, and you see that the erythrite is most abundant at the depth horizons where we see the highest cobalt concentrations. So here are a list of some of our outputs to date, and we hope to add to this list very soon. And with that, I conclude my talk. Thank you.